Hmm. Wow. Super Olin time. All right. Should get started here. I have Colin's fancy clicker today, so I know it's serious. All right. Oh, I don't even have to be over here. I can just move around now. All right. Wow. Stress transformations, part 2. Woohoo. We get sight. All right. We remember this, right? We talked about last time. Our handy stress element. Yeah. Did this fall out of people's heads over the last couple of days, or is it kind of sticking? Sticking? Sweet. Excellent. Love it. Okay, we're gonna go back to our favorite practice problem once again. Hmm? Are we doing it? No. You've been there, done that. I trust that you are able to plug and chug. So yeah, we're going to now look at the kind of wacky way of doing this. Basically, there's a graphical method for doing stress transformations and visualizing this that is super handy and not taught at Olin. It is taught at Olin now? It really? It was at some point. Really? Oh, maybe it was just Emily Tyler.
It might have just been Brian's Excel. It's also really wacky. It didn't really stick. But maybe
okay.
you can do a better job.
All right, we'll see if we can do a better job then. Excellent. All right. So if you oh no, I clicked away from the thing. That's not okay. All right. So we have axes. These axes are sigma and tau, or normal stresses and shear stresses. So, normal system axes. So we can plot now these points on here, right? Because they're two different. You see, there's two different points here. So what would be my 2 points that I'd be plotting on this axis over here? Yeah. Yeah. Exactly. Yeah. So basically, if you look at this and you only look at one face, basically, this face has 400 shear stress and 1200 normal, which gives us that point. And also, I've seen the sign convention both ways for this. We'll get into that later, but I think most people treat it this way, where I don't know, most people say that positive shear is down. So this actually should be positive and that's negative, but that's, I don't know. I've seen it both ways. Yeah. So as long as you stay consistent, it shouldn't matter. It won't change your results. Yeah. So we have, so we have normal, shear, we have our points. And then the magical thing happens. And you draw a circle. Yeah. Magical. Okay. So remember, last time we talked about principal stresses, right? So what is the condition for principal stress? What's happening with shear stress when where the principal stresses are? They're 0. So what does this line mean? What do these intercepts?
Your principal stress.
They're your principal stresses. Whoa! Yeah.
Okay, so this isn't the only unique circle that you can make for this set of points, right? Because you need group points to define a unique circle. So are there multiple?
It has to be. There's no way that a Mohr circle cannot be centered on the sigma axis.
Oh, okay.
Yeah. So the third point is the center point between the two. Yeah. Or your average of your normal stresses at any angle. So so for example, if we rotated this, right? So we know that this is one orientation that corresponds to these 2 points. If we rotate this to the principal angle, we're gonna rotate around these 2 points. So it means any position on here, any pair of positions on there is a valid orientation for this state of stress, which means that if you are given, if you can basically solve, well, we'll get to that. Okay. Yeah. And notice that matches this. Yeah. Yeah. So you can skip that and just draw it. Just great. Now, what are those at the top and bottom points? Yeah. Those match that. So note this is max in plane shear, not max absolute shear, which in this case is out of plane. And we'll get into that in a second. Yeah. So the value of the peak shear value is your peak shear value. Yeah.
You also gonna mention how you solve for the angles for
That's coming up, I think. Let's find out. Desmos, again, pretty nice and actually helpful for this. So in order to do that, you can use these equations. So basically, it's just, if you look at the equation up there. Oh, wait. Oh, more better. All right. If you look at the equation, you have this, which is this is basically the X value on the Mohr circle plot, minus the average stress, which is the average normal stress, which is your center point of your circle. And then this value is your shear squared, right? And is your Y value, and then R squared. So it's just the equations for a circle, just broken down into cool things. Another way of looking at it, yeah, anyway. Yeah, and here, sign convention. Again, I've seen this both ways, but as long as you're consistent, it shouldn't matter. Yeah, so this is how you find angles. So, because remember when you rotate the stress element 180 degrees, that's actually a full rotation through all of the possible stress states or stress orientations. So this is actually 2 theta, right? Does that make sense? How does that feel? Kind of wacky. You can prove it to yourself with math later. Like by just like floating in Desmos and like looking at the numbers, but yeah. So basically, to find you can use the angle. You can find the angle graphically by doing this, and then likewise, you can also solve for any. You can solve for the normal shear stresses at any angle by doing this. You can just basically like distance of the triangle kind of thing, and that's exactly what the actual stress transformation equations are. They're just, if you go back to, we don't have the other ones up here, but yeah, it means basically like principal stress equations are just the same thing, right? It's just finding, it's literally, man, I keep forgetting. It's the average, right? So it's the average of the stresses at any whatever normal stresses at whatever orientation you're at, plus the square root of something squared plus something squared, which is Pythagorean theorem, right? So this is literally just the distance. It's basically, it's the center point here plus or minus the max shear stress. Yeah.
Wow.
Wild. Cool. How's that feel? Is that making sense? Yeah. Cool. Yeah. So you guys are gonna draw one now. Yeah. Feel free to also go to like a blackboard if you want to like show the circle drawing skills.
Oh yeah.
Yeah. Woohoo! Yes, we're moving finally in this class.
You want to do it at your desk, we have to move to a different desk.
Great, and all of your stuff.
Sure. You could also relook at your type here, but yeah.
You gotta jump while doing
how
that's
my
the trick. Oh, look at this.
I need a photo of this.
Oh yeah, there you go.
Ellie, how good are you at drawing circles?
Oh, that's pretty good. Yeah. Now plot some axes on that circle. Let's see. You're holding the equation. Yes.
I am personally a big fan of drawing a circle and making your axes.
What you do with the axes and draw them. It's like a shimmer, you know, yeah. Highlights.
Wait, why didn't we draw one? Totally, yeah.
Because otherwise it's not a circle. If you draw them both above the axis. Oh, it's also if you, it's the direction, like if you're ignoring the other normal, stress, if you just look at the one normal stress, it's the like the orientate or like the shear on that one face basically. Yeah. So it's like even the same state of shear, like the same orientation will be the opposite to the X and the Y. Oh, whoa!
Whoa.
You gotta use on nothing.
Whoa.
Even the volume thing works. Draw the circle and like note where all the stuff is. And then if you feel so inclined, you can like do some calculation and verify that it's right. Yeah.
Recording.
So we have it. It's going to start in the case.
So X, Y is at whatever starting orientation. Prime is another rotation. So it's the same thing. So like X, Y, the primes are the orientations.
You're finding this and then.
Yes, so, okay, so in this case, prime is along where as you rotate the X axis changing, so like the X, Y that were given in the starting equation, that X, Y never changes, it's the starting Y. The X prime, Y prime will change it. The values basically as you sweep along and plot.
That kind of makes sense.
Make a circle.
I don't got it, but I don't. Florence told me.
Do you remember what that is? Yeah, I'm something loud.
Yeah.
So.
The convention is probably the most confusing part of this.
Like if I ever something, you can do this. I'm not even there. But yeah, this is a little stretches. Shear stresses within shear. And you just have some stresses. Basically, this axis right here, it's just the intersection of that circle. So that's and if I go back to calculating like here, I now have this 2 and now I can really calculate and just visually represent it. Similarly, if I now go back to my goals and axis, the y values would be stress this is exactly. And it was also essentially it's just kind of a visual representation of it. You don't have to see it's like a plug and play. The plug and play is so Desmos is a great way to represent this. It's really key for the circle. It's a great thing. So here's the center of the community. It's like stress. That into
Okay, so X and Y, so X and Y are the ones we're given, that's the orientation we're given. The X prime and Y prime, oh, I raised my prime, but it's nailed on me. Like X prime, Y prime can rotate, that's what I'm with, right? So as we rotate this, it's gonna fall, we're gonna like sweep along the pocketable values here. Which means that over time, I'm vision as it comes circle. Like I like to do any line sort of like that has pockets. like I've assumed like science.
I just sometimes so open that lab.
So yeah, based on the time, whatever orientation you're kind of looking at, it means it can sweep across this, which means you can sweep across that. Water with two sides. No, no, yeah, so that is when you. No, yeah. Yeah, I did the exact same thing. Double here.
Cool. Now.
Oh, I think so, yeah, it was just, yeah,
Right.
James is talking about it.
I do. Oh, I lost my cookie.
No.
No. Oh, I went to
Ricky. Also, remember.
to Zoom.
Well.
All right. Do we concur? You make a circle?
No spoilers.
Huh. I may have calculated shear wrong somehow. Or, all right, I'm definitely wrong then. I didn't calculate this like.
I think
I got it.
yeah.
Different shearing.
Got it. I used the calculator thing. I probably should took it off the calculator. Off the bat. What? Yeah.
Whoa.
We'll see. We'll see. Contentious.
Would it not just be the difference senior
Yeah, it did. Yeah.
higher
Yeah.
principal?
Also, why did
divided
I
by two?
Huh?
Is that max out of the plane shear stress?
Oh, it definitely is.
Yeah.
All right. All right. All right.
Yeah, that's exactly what it is.
It's exactly what it is.
13.5.
I definitely did.
Your coordinates are wrong. It's
Yeah.
it's
Yeah. Yeah. All right. All right. I will fix all of that later. Nobody look at the slide. Moving on.
I just wanted to include this quick bit about why we're talking about Mohr circle. Mohr circle is like super useful way to like make a very quick understanding of the stress state. It's a great way to visualize it, but also like if you're solving for the stress state of some element you have in load, you're not just gonna like without. It's like in some ways it's not antiquated, but it's like has a similar energy of just using Bowling rule to solve problems. Like it's useful, but like you should have a better understanding of like how to actually use these values. The reason why we're still going over it is that next week we're getting into like we're done with all review. Next week is brand new content, all going forward, starting with static failure theories. Mohr circle is a great way of visualizing how principal stresses work, principal max shear stresses, and we'll get to it soon. Actually, I won't spoil it. He has a good bit. And like what you'll see is that there's more failure curves. There's like more static theories. Like failure is a very not unknown, but like a very like statistical thing. There is no one correct way to go about it. But what you have is several models, and on the right we have a flow chart of like you are going to describe your stress if you are working with brittle material or failure or ductile material, and you're going to go down this flow chart and figure out what is my approximate way that I'm going to like use my failure theory to get an estimate. And Mohr circle is kind of like a good stepping stone to get to that point. Because like a lot of these end up being like graphical methods of understanding. Like, okay, am I like in my failure regime or am I not in my failure regime? So I just wanted to throw that in there.
Makes sense. See. All right. It's time.
Everyone look underneath your table.
Oh, so good. It was so good. All right. So last class on chalkboard towards the end, we kind of went over the general thing, but to recap, 3D stress elements, actually all stress elements are 3D stress elements. We've just been ignoring the depth right now. We've been saying that everything that is not, we've been saying that everything that has a Z in it is 0. Poof. So that takes out all of this stuff, right? But in reality, all stress elements are 3D. You know, we live in a 3D world. Shocking, isn't it? Yeah. Just start debating dimensions, actually. That's the right use of class time. Okay, so yeah. Does this make sense to everybody? So we have, it's the exact same thing, but there's just 3 of them, basically 3 of the 2D ones stacked together, basically, right? So if you look at, for example, the what is that? The ZY plane right here. We have a normal X coming out of it, and we have XZ and ZX are these two normal stresses, right? That makes sense. So it's literally the same thing, just stacked together, and the normal stresses kind of interact between them, and everything interacts. But yeah, yeah, 3x3 matrix and such. Yeah.
Why are some matrices called tensors?
Okay. So every matrix is a tensor, and not every tensor is a matrix, is the way I understand it. Everybody formally calls this a stress tensor. It is a matrix, but everybody calls it a stress tensor because that's the way it is. Talk to John Geddes. Yes.
This is so beyond our non-existent pay grade.
Yeah, yes, yes. Right. Yeah, so a tensor can be any number of dimensions in any way, is my understanding. And a matrix is generally something like this, is my understanding.
You could call it
Not sure about that one.
No, I don't think so.
Uh,
I think you could represent it as.
I think he represented as
You
one.
could represent it as one, but I don't think there's just a one.
I don't think.
I feel like that would be. This might be so stupid, but I feel like that's kind of like calling a map a street, where like it's how we represent the street, but it doesn't make it one.
Maybe.
Like a matrix can represent a vector, but I don't think it is one.
No.
Sorry.
Semantics.
Yeah.
Yeah, this is semantics. That's
Okay.
go to good point, John.
Yeah. Yeah. And then, like we said last time, like basically this for all normal and real and reasonable things in this world, this is going to be a symmetric tensor matrix, whatever you want to call it. Big vector. Definitely not that one. So XY and YX are going to be equal, and XZ and ZX are going to be equal, right? Because those are the same things. It's the only way they can be equal. So unless you're doing like dynamic stress elements or something like that, which sounds like something you'd never do. Yeah. Okay. Yeah. So another important thing there, when you're thinking about the 3D state of stress, if you to get the principal stresses in 3D, all of your shear stresses need to be 0, which leaves you this mystery third. Ooh, there's another point somewhere. Ooh. All right, that makes sense. So in order to get the actual principal stresses in 3D, all of the shear needs to be 0 in every dimension, which it has been, but now we're going to explicitly state that, and we'll see that in 3D now. That makes sense. Okay. All right. So this is our same 2D practice problem, and this is it like rotated, right? So this is our 3D version of that same practice problem, and that's the 3D version rotated around the z-axis, right? Because we know that right now there's no, because we know in the problem we're given that there's, because it's 2D, we're given that there's nothing happening in the z direction here, right? And so we know that sigma z here is 0. So we can rotate it around that z to get this, right? This is this new orientation in 3D. So in 3D stress, 3D elements can be rotated in any axis, right? They can be rotated in any direction they could possibly want to. In this case, because the one coming out towards us is 0, we can just rotate around that z-axis to find, because we already know we can find our principal stresses by just rotating around z, right? Because that's what we have been doing. So all we've been doing so far is rotating stuff around z. And so we know that we can already get 2 of our principal stresses that way, which means we can also get our third principal stress that way. Does that make sense? So what would our third principal stress be? 0. Woohoo! Yay! Okay, now where's it going here? Yeah, the origin. Oh, wait, whoa, hold on. Whoa. Okay, yeah, another thing. So basically, what face of this cube does this circle represent? Yeah. So this circle, the one we've been doing so far, is this face, which is the one we've been seeing this whole time, and it's this face. So, like I said, you can add that point at the origin, which is a third principal stress, right? But it's not on that circle, right? Okay, so where would our wait, hold on, where would that face go? So, okay, so for this face, right? For the purple face, you can look at this, right? So we have sigma 1 and sigma 2 here. So those are our two like normal stresses, right? And those are these 2 points, right? Because there's no shear as we already defined. So that's this point and this point. And so our third one is 0, and we know that's that point. And so what's happening on this orange face here? Like, what are the 2 normal stresses for that face?
It would be a different circle from it.
It's a different circle, yes. No. Think about which principal stresses they are. So if we're looking at this cube from the side, from the orange side, yeah.
Would it be 2 and 3?
Yeah. Boop. Whoa. All right. Okay, and now, where's that green face? It goes around the whole thing. Boom! Whoa!
Gabe, that brought me a lot of joy. I just
All right.
also, Nathan, this is a wonderful way.
I'm glad.
Yes.
All right. Is this making sense? Yeah? Sweet. Okay, so we have all of our principal stresses, all 3 of them. We live in a 3D world. We have our so here's the thing. This is what I messed up on the other slide. What is this red dot? So this is our max shear, right? But it's max shear in the purple plane. What's the max overall shear for the whole thing? The top of the green one. So this is the in plane versus out of plane thing. And I have a way of visualizing it, and we'll get to that at the end. Yeah, I figured out a way with the thing. Yeah, cool. Does this make sense? Good. All right. So remember on the we go back to this. So if we're just looking at the 2D version for a second, remember if we rotate any angle of this thing, it's going to have, there's going to be 2 points on this circle as they go around, right? So what happens when we go back to the 3D version? Where are all the points going to be in this version? So like we already know that if we just rotate it, we have our stress element, we're rotating it about Z. That means that, we have 2 points that are going to be, going around the circle on the opposite side, like they're afraid of each other. And we already know that there's going to be a point stuck at 0, right? Because that's going to be the only thing happening on the other face. It's like there's no shear and there's no normal stress happening on that third face. Well, the face that we're looking at, but yeah. So we know that there's nothing going on in that face. So that means there's going to be 1 point there, right? One face is going to be there. One face is going to be over here somewhere. Or actually, and for this example, it's the black dots, right? The black dots are this face. So we have the black dots, and then the third black dot from this orientation will be at 0, 0. But they can't go everywhere within all these 3 circles, right? They can only exist in a region on this plot, which is that. Does that make sense? So in this orientation, we have a spot here at this like infinitesimally thin little spot here, and we have these 2 dots, right? But if you start rotating the 3D stress element around more axes, then you can start moving those, like in that orientation, the normal shear stresses are, you can put them anywhere in this green region, basically. Not every combination of them will work, but basically, as you spin it around, you can see the 3 faces represented at different locations around that. That makes sense. There's a way we can play with it. We'll get to that. That's good. All right. Yeah. And then there's our max out of plane shear stress, which, as we can see, magically is the same as this.
And it's going to happen next.
Yes. Which we saw on the original very first problem, where we had like the simple beam and tension. Remember, it was like 1 KSI of tension, and we rotated it and we got 0.5 max shear, right? Yeah, in that case, because there's no other normal stress, there was no, that it means that the, because like this value, like the sigma y value is 0, which means that the max in plane was the max total shear stress. Not like, so yeah, yeah. Cool. Yep. Yeah, so there's all our values and they all match up, which is great. Again, Desmos pretty awesome for this. It makes it pretty easy to see and pretty fast. Yeah, it works, math works. Okay, so now you guys are going to complete the 3D Mohr circle for this problem that you guys write. So if you can go back to your blackboards and draw the other 2 circles. Oh, dramatic Mohr circle.
You guys understand if Moore's circle is becoming so powerful, whether that's I know I'm so serious. That was the best video you ever seen. Like that just like makes everything. The graph to stress wording so awesome. Yeah, that was sick. I think that is 100%. Because like this is one where like I think you're talking about fails you.
Yeah. Nice. Amazing.
Yeah.
Woohoo!
Yay! Oh, Jack.
Oh,
Wait, how did it out?
Yeah.
Oh, wait. No,
woohoo! More circle. Yay. All right. Excellent. More circle. You might be asking, how did I make this plot? We'll get to that. It's fun. It's really fun. All right. Yeah. So, okay, to recap a little bit, more circle in 3D. These are your different planes, right? So the original one we drew is your in plane, right? So that is that's the plane we're looking at the whole time, right? And then you have the other 2 circles, which are your out of plane circles. Yeah, and so basically it's, the first one was 1 is sigma 2, the second one was 2 sigma 3, and the last sigma 1 and sigma 3 as the normal stresses for that phase. Okay. Hence the
he had a slide on this earlier. A convention, because it might get a little confusing when you see this. Convention has your sigma 1, sigma 2, sigma 3 stresses go from most to least. So you have sigma 1, sigma 2, sigma 3. Like
always.
Yeah, that's always how it goes. Like the maximum magnitude. Even, do you have an example where you have a negative?
I'm not sure.
Okay, we don't go over it in this class, but it is possible to have a stress element where this entire thing shifts over and you have a negative.
Yeah. And
it still goes like from right to left of your greatest value to negative value, which will be important to distinguish when we get to static figures.
Yeah. Yeah. So just imagine, like, I mean, you can draw it actually. I mean, if you guys want to actually, how about this? How about you guys go also, you can like state your seat or whatever, but draw one of these, like imagining that the, I don't know, let's say the 10 KSI is negative. So compression rather than tension. Yeah. Or go to the blackboard. Yeah.
The outer plane step is always the greatest.
No, it's not necessarily. Draw the more
With the-
circle.
with the-
Yeah. So if one of these is 0, like our first original problem, it means that the maximum, like if you think about it, like the maximum possible shear in that case would be if you just rotated 90 degrees and just pulled directly on that thing into parallelogram, right? So all of the force in the entire system is pulling it into parallelogramming. When you have 2 that are going the same direction like this, it means that there's an orientation in 3D such that you have even greater. So like basically in order to maximize the shear stress, both of these forces need to be pulling on the face in a way at a weird angle that maximizes the shear. So when the two, basically when these two are going the same direction, when those two are going the same direction, there's a weird orientation that causes like even more shear than it would be if it was just aligned with one of those, or like in between the two. This is really visualizing. We'll get there.
Wait, so if this was -10, it would span like, and then this would be like the big.
Right. Exactly. So if one of these, so if the 10 is a negative sign, that means we can plug it into the calculator at the end. If one of them has a negative sign, it means that the in-plane circle will be the biggest circle, which means the in-plane shear stress will be the greatest shear stress. Right? Because like if you're, does that make sense? We can draw it out and visualize it. But like that.
But does that change if you've got like a rotation around like multiple axes?
This is a rotation on multiple axes.
Really? Okay.
So like, okay, so imagine this, right? So this right here, so we have like a y and x those are given, right? Those are fixed values from our original orientation.
Yeah.
There is some y prime and x prime, and that's what we're kind of sweeping across to create different things. Remember last class we had that plot of shear and normal stresses, and it was like two sine waves offset at 90 degrees. Well, if you plot two sine waves at 90 degrees apart, you get a circle. Whoa. So basically the y prime and x prime, like the theta angle we're sweeping, creates that sine wave. So if you rotate in the other two directions, that causes the other two circles. And so when you put all three of them together on the same plot, you get, cool. All right. Okay. So two planes, same circles, right? Is this right? Plane stress. Okay, so here you can see, here's exactly what we were just talking about. So in this case, the third, like one still like basically the third principal stress is negative in this case. Like Carlos was saying, it's P1, P2, P3, or P. Okay, cool. Anyway, so the first one, the principal stress is in order, which means that the one that's 0 is bigger than the one that's negative, right? So it's always in that order. And so actually, I think no. Anyway, so in this case, the in-plane circle, which is the solid one in both of these, right? So this is basically like equivalent to what we did like our practice problem that we did the first time. So it means the outer plane was the max absolute shear, and in this one where one is negative, right? So like there's compression and tension happening in two different axes. It means that the max absolute shear is going to be in plane. All right. So this is a kind of a useful thing to think about. You can draw this out for yourself. If you're just like coming through any practice problems later, if you want to think about this more, we're going to kind of go through it because we have other stuff to do. So pure axial stress. This is what we did. Like the very first thing we did with stress transformations, right? Beginning of last class, it was just a beam and pure tension, right? So that's this. So more circle for this is like starts at 0, right? Because there's a like P2 is basically 0 and P3 are basically 0, right? So both of the second normal stresses are 0. And so basically like all three things are going to be stacked on top of each other in that case. Or I guess there's only going to be one circle. Yeah. And then like I said, if you're rotating 90 degrees, it's going to give you your peak shear, which puts it at the top and bottom, right? So this is the more circle for our very first day thing.
You could also think about like if this is tension, then for compression it's just flipped on the about my y-axis.
Yeah.
So I'll have it like it's totally negative.
It's also worth mentioning, like you see that also we just went a little bit, but that sigma x equals P over A, like that's one way to represent like my normal stress in this area is like for this 1B tension case is that, which is like where our formulas for stress come from.
There's something here about like how you need to divide the angle by 2 to get like 45 degrees.
So go ahead.
Okay. So I think what you're confusing is, so you remember, actually, do you mind going back like 30 slides? Sorry.
I could use the clicker more. Aha, yes.
Yeah. So, you remember how on Monday when we had a 2D stress state like this, if we flip that 180 degrees around, we end up with the exact same stress state we started with?
Because all the forces are equal and opposite, right? So if you rotate 180
Yeah,
degrees, you have the
just
same
a
force doing the same.
Yes.
Yeah.
So if we do 180 in our stress state, that it's equally the same. For our circle, however, we have 360 degrees of rotation. So that's where the 2 theta p comes from. And so that is just relating to when you're calculating the angle between your like for your principal plane stress. Yeah, before you leave, I'm going to text you a link. I'm just filling it out when you're done.
They not overshoot. That would be catastrophic for the flow. Okay, right. So we're going to do a problem in a second that involves torsion. And so just a quick preview of what that might look like. For pure, for pure shear stress, right? So that is like pure torsion is a good example because it's kind of pure shear stress. So if we have a tube right here in torsion, and we have our stress element on the side here, it means that there's not going to be any in original orientation, there's not going to be any normal stresses, right? Because there's nothing pulling on it and there's nothing pulling on it or pushing in it. So it means that our initial conditions in this case, keep missing the laser button. In this case, and from our initial like XY, that's going to be these values right here, right? That's going to be perfectly up and down. It's going to be pure shear, right? And then if you rotate that, you can rotate it 45 degrees. You end up with your max normal stresses and no shear stress, right? Because your stress element is now aligned on that 45-degree angle. Also, think back to the chalk day 1. Carlos snapped the chalk. It was on 45-degree angle. Whoa. Maybe it's connected. I don't know. All right. Now let's do this practice problem. So this is kind of a wacky problem. I would highly recommend Blackboards for this and working together. I have not even gone all the way through this problem. But I think it's going to be fun. The answers are also in the slides. So if you get stuck, like talk first. And, if you look at the answers first, you'll learn less. So do a favor to unlearning and don't look at the answers until you're like super stuck and you've thought about it for a little bit. And then once you go, there'll be the aha moment. And then that's where the learning happens. So yeah, so it's basically this kind of right angle thingamajig here. We have a kind of round beam that's connected to a fixed plate at the fixed wall. And we have this kind of plate at the front, it has a heavy force on it. We have some material properties and some dimensions and things here. So this kind of is tying everything together, right? So we're bringing a little bit of beam bending right here.
You're gonna need a few equations.
Yeah. So we're looking at beam bending, and those are actually on the next slide.
Oh, lol.
Yeah, so you'll have to do some looking at things up a little bit, but I think most of the stuff's here, or in the next couple slides with the answers. So yeah, so head to a Blackboard and probably have these slides handy so you can flip back and forth between these two. And yes, exactly. Thank you, Carlos. Yeah, that's good. So basically the object of the game is to find the applied and principal stresses at A and B and draw a Mohr circle for points A and B, right? So those are those 2 points up there, A and B. Yeah. Break.
And as a reminder, I for beam bending is your second moment of inertia. There's a table. We're just using a circular rod, so very easy to find. And J is your polar moment of inertia, which is used for your shear torque calculation stress. The Y is like the distance from your neutral axis, and the R is your radius for your circle or whatever thing you're torquing. Sweet. Wow, are you?
Oh, yo. Yeah.
Whatever.
The Tesla folks. Oh, sweet. Yeah.
It's just a neon James.
James. Okay.
Can you refresh the slides? I added a TA slide.
Yeah. I will actually hold on.
Actually, sorry, no, this is about time. I realized.
Yeah. I can do it because I'm going to pull up the stress calculator so I can do it.
I'm also gonna fix that first one circle for you.
Oh, please. Thank you.
Don't forget to take this slide.
Oh, I should have taken the last one.
Like the actual.
Like back of the line. Oh, like cross section. Yeah.
It's a napkin. I'm not even going
Oh, okay. The napkin. Oh, I thought you.
Really going to town.
to.
Really is going in.
It is a little crazy.
My understanding is on the loader. Sure, so. I guess maybe. Yeah. Because I think it's for. Like, branding.
right. Oh, keep going down. Yeah. That should do it. And. Oh, it's not very good. It's gonna be more text slicers. I always just look up, like, first I'm a fan of Engineer Toolkit. I just look up Engineer's Toolkit. Second, inertia. Yeah. So there's that one thing. Yeah. So does that include? So the way I would personally think about this is, so like you're finding the max. I would only focus at eight. Okay. We're gonna find the max stress. We're gonna find the max stress line. What do you think? Like, let's start with our just basically. What do you think the maximum stress the extra is caused by? Yeah, yeah. So like we don't really have any forces in the pure extra, but we do have a force.
Downward is downward force.
So how do we represent the stress?
Let's start with the stress.
Anything that's what's our formula for that? The max. So the way I would think about this is, the way I usually go about more circle problems is I want to find, okay, what is my first point I'm going to define, and then I'm going to define my second points after that. I'll then find my circle, and once I have one circle, it's actually not that bad to get the rest of the circles. So let's start with just the first circle and the first stress. So I would just start. It doesn't even have to know this, right? I would just start with your sigma and tau. Yeah, your x and y axes. Yeah, and now go ahead and label it just sigma and tau. We want to define our first. We want to find our first like bending moment. We're going to say that is sigma x. Right? So just roughly, what is so we're going to let's calculate that right now.
Yeah. If I think about like my length, like force. Yeah.
So we have
That means the moment
for my help or like how.
So the MC is I would just
Exactly.
you could do
What is your that's what we have the force.
I think and I would do this where at the top, like that. So this is like the first part of the solution. Given my arm, this the notation is. To find well, so we're not going to so you have a state, you know your two zones.
what times of weight we're gonna use now.
So like the basically bending.
Correct.
So bending is on that. So bending is here. We have
We're gonna use when we calculate the shear stress or.
and what's more, I was just talking about that. Okay. Because we might try to toss it through the process. Get the max value thing of the bending stress for. Yeah. Okay.
Yeah.
So you have to.
So if I call for the reaction failure,
Sigma
just.
hat.
Yeah, well, the thing is, yeah, I think you can agree with it. Because, I think that's fine, because the only time I did areas is that occurs that after bending, everyone does not get worked out.
Right.
Like that. So it's like, I think, it's like 1 second.
Well, no, but like literally.
The eye of the, but I think.
Yo. The crew. Sorry for late for class. Yeah, look at it. Someone see you again, but you're. All right, chalk and talk, bud.
Oh, no.
Get up there. No. Hope it will be incorporated. This is actually the last day right now. The material is now solids.
So we want the,
Yeah.
this one.
So, like, you having a simple sign. This percent of it in right. Load maybe built areas, but
So.
like kind of able to be
Trying to find.
But it's also. So. Like I could. Bias.
Sure.
So you actually want to use your second.
So is that your.
The cross section. So what I would do, because engineers toolbox. Second moment. So your first moment of inertia is just like. So actually, that's your second. Your first moment of inertia goes back to. Physics, where instead of your mass, which is your distance away from your lens. This, so this is going back to. So our area, sometimes called the area of inertia, second moment of inertia, not here to be high. So
There's gonna be.
yeah, it's a high.
So it's also the.
You'll get there.
Slowly but surely.
That's probably. Jesus Christ. And, yeah, I guess I'm sure we are. Like, use.
Yeah.
Right. We don't really have it going on. Well, yeah.
So, when you're not even starting that.
Yes, but you want to be very careful because you have. What does your integration say? You show when. There's some. Yes, it is. That's sort of, but you know, that's probably not. You're actually looking at yourself.
I would keep as many values as possible.
Where are those? There's the shear. So if you wanted to do the actual, so if you wanted to do where you're playing here. Oh, that's actually. But actually, so like, let's try we have, another big 9 inches in our X direction. And 8 inches. And 0 inches on the Y. There's a lot of lines. So then I have like straighter out. After 0, I have. And those very times. Now we let it find. Because, yeah, exactly. Like, they had. Oh, yeah. And then shoot, I would shoot. Oh my god. Zero. Zero I had. I had. In that box. Yeah. Yeah, at least. Right. Oh, you're gonna. Yeah, I think zero. 0. I'm gonna remember this year. I. So I think we just, so in like, they wanted to find a very target. So like, you can like, it would help me personally. I think this, if you know, it's okay. I think like they're just gonna say like this force, like we're gonna use this length for this length and we're gonna this length for the force. I so yeah, just remember you're sharing this. So if it's about the effects, right around. Sorry. No, it's not right. Oh, then that's just that. Yeah. Yeah. That's why it's. Right. Well, so and then oh, right there. Why is here? So let's see this. Why? Yeah. So yeah, that means it's gonna be the raise. Okay, cool. So yeah, we're right now. Yeah.
That equivalent, so I find, doesn't mean not, usually I see it in this form, but that would kind of. Okay, usually I see it in this one, but that it's line is. You have a school. It's probably the 2%. So your sheer. So can I see one of you guys? So I go. I would type in. Back. I did. Leave the. And so are we can talk about? Yeah, because we're. About. Yeah, oh, okay, sorry, no. You know, very nice. No, so this is where the actual formula is. I like it. Sections. First of all, cross section. About the access. There we go. Yeah. So you need either one. Oh, it's not. The one. So like, so you do doing it. Yeah, it's not with the whole. It's okay. I mean, so then all of this will actually like the figure out what. I don't know. We found things. Cool. They're helpful. Yeah. And we get this time to like so. So I think.
Trying to do more things on our. Well,
We found the things that I think are useful.
but we don't know how they're.
Yeah.
So we have stress.
Okay.
And we've been just like trying to add it to our office. Building is stress element.
So, it's just almost necessary. Think about which of the forces are acting on which.
So this would be really.
Really care about the top. So yeah, because remember, when you're talking about a surface, you can't have any shear or forces. Resources, anything. I guess. So then the edge of the thing, it's really gonna. Yeah, basically,
So 8.
Maybe there. It's actually, oh, right, because it's free service, you can't. Supposed to be 6,000. Oh, there. So think about which, yeah, okay, that sounds good. Forces calculated.
That's fine. Well.
So yeah, so the economy is instead of 1,000, it's like 1,000 pounds. Usually, yeah. It's not a difference, or not, actually, that's not a difference, it's. And then the bigger thing. Yeah, they're not numbers. Then, sorry, yeah, if I'm not doing my work, yeah, so if stress, stress, always rocking areas. Well, it should be a B. We got about 18,000. That sounds good. That's a stress measure.
remember your research. Right. I would just drop. I think it's cool.
Okay.
Let's go.
I don't know.
Alright, I wanna start thinking about the shear dress now. So let's start thinking about, like, it's something. Yeah, could be hacked. Let's figure out then what the other one is. PR. Yeah. We got you. Here. Okay. T is gonna be your torque as that component, and that's gonna be your explosive magnets. It's like. Oh, I forgot. Yeah, exactly. Yes.
So that would be the.
That's gonna be range. So we're just being. Sorry, so you guys like want to drive or hands down, right? Okay. Let's see. No, we're gonna calculate that. So in a moment.
Okay.
That's what's really fun. We're just like forward, just like what is your lateral arm? So we're gonna do negative 1,000. We know that.
I think they end up being.
Yeah. 8 inches.
Yes.
And these get minus to 1.5, but that's the package. That's my R. And then let's figure out what J. J is your polar moment inertia, which if you go. Yeah, if you go to engineer's toolbox with a polar moment inertia, you'll get another useful word that's just like that.
Is this your?
Oh, yeah, yes. Yeah, so I'm doing. Okay. So if I can read the calculations enough, it starts getting familiar. So for me, I know, for example, like. That's what I, that tells me, let's see if it's correct. So going down. Going down. So like you said, why sharing my person?
What do you get over?
Oh. I D to the fourth, but that's right. Yeah.
Oh, so that's the one we used here.
Yeah, so you guys accidentally did that. So. Yeah. Second moment of inertia or the moment of area is similar to your polar moment inertia. That is polar. I just think like radius. I assign that to second moment of inertia. I'm just going to assign it to that phase along this. So there's similar things. Like, you remember like high school physics? You have your inertia. It's a very similar concept.
Okay.
They really, it's just, yeah. I mean, when you get, the way you do it is you start saying I and J.
It makes sense.
So then you calculate this. Oh, no,
Oh, I get it.
We do need lead time. We understand. It's second.
Yeah.
So today we're supposed to have like engineering blocks like sample. We're gonna do a walkthrough of that. That sounds perfect to me. I don't have a negative.
Oh, I thought it was. It'd be a negative.
Oh,
Never mind. I just, my bad.
Yeah.
Yeah.
That's not very.
Oh, okay, so
Sure, yeah.
we just went in opposite directions now. That was- and they went and slide.
That's awesome. Okay. All right.
but you have to.
No.
Which is why.
Are you good at racing all this?
I-
Yes. So. So here, let's rip it out. Our confidence. Pretty good. Yeah. Good.
Yeah, I mean, so we're kind of throwing. But we're in. There's lifeguard.
Yeah. They were talking about.
Well, I saw you mentioned the back. He was like, Ron, he's trying to.
Very consistent.
Across the diagonal. We're kind of on the well, and we were like, wow.
Yeah.
Yeah.
I mean, nice. Professor.
Yeah, that was fun. Yeah. I don't have like anything, but I was.
You wanna do it?
Yeah, so I think actually a reader box.
Two, not putting.
Some things are pretty. The taxes.
Yes. Yeah.
Yes.
Thinker values are okay, that's fine. We're gonna. We'll look at right now. I get in the solution phase magically. White-ish.
So is that transfer shear stress?
Oh, I know.
Things you calculate.
They're looking at,
Are new facts on the thing.
so that's it. This calculation. It's, because remember when I talked about for, like, if you have a beam and bending, you have one axis above it, it's either tension or shear, or sorry, tension or one that's below it. So not for the Tesla 9 convention is that.
Yeah, right. So wait, when you,
Sign convention says.
Oh.
Tension.
Looking at those.
In this beam bending,
And then, I was thinking it should be like
down,
down.
fall.
I did 24
So
years.
technically, that formula. Yeah.
Okay.
Maybe it'd be a line.
This is 10.
Missing a line.
This is the volume.
Oh. Well, no, actually. That's fair. We're actually going to get transfer shear right now. So transfer shear is, remember when I was talking about that beam bending, like you have a stress profile that looks like this. Where is the maximum transfer shear? So if you get anywhere here, where is actually,
This
Oh.
is.
so I think it's transfer shear. In number one, we're calculating, right? And so at free surface here, your stress must be.
So we thought
So
one is like after you have.
even if we were.
We have.
Right here,
It's like.
if we look over here, so I don't know what, we look at the value transfer here, and it's like.
remember the previous slide I said?
We transfer here on things and fail numbers here. It's like.
Here's your.
But like most of the time, we're bending stress. Here's your.
Okay, but that would be.
Like
The
first,
stress element damage. Looks more like.
it's gonna be greater than.
Basically first.
Okay, so it's the neutral axis.
Really can't tell towards.
So we're. Yeah.
So we use that middle.
So let's start with, well, so yeah.
Research. The first year,
On the page, you're accessing out of the page, right? So,
yeah.
so actually,
Like, look at the distribution. And I just like, if you had to. I don't know. It's also just first year is where you're taking a specific. It's like average service, so it's kind of like. But that's not into the theater. Like, that makes sense, like, we're trying to find. Yeah, so, let's do. We're gonna orient it,
Because there's no portion, there's nothing taken.
we're gonna orient this, normal stress when you're perpendicular. If you're at 45 degrees, it's a different story, but in this orientation, which we're in right now. There's no normal stress that comes from. 14 degrees.
wait, so we're looking at,
No, sorry, this will be. There is not that context. Because there's nothing.
we're looking at.
So here, so like this, yeah, there's nothing, it's not like being pulled in one direction about it's two A right here, it's being self-kind, so like, imagine like if it's twisted. Yeah. Right. Oh, every little square you draw, that gets like. Yeah, so then this. Now. What's your next direction? If you're twisting.
There's direction.
This, for example, there's nothing. There's no normal force, right? There's nothing pulling the line. Nothing, like, all forces are. Forcing out. Yeah. So you're now taking them. Sure.
And that's like,
And again, it's here, this is acting at a curved surface, so we're just kind of like, imagine suspend this a little bit. So imagine no bolts. So we're gonna do this. Hold on, right? That's like,
We calculated-
normal, right? And you do it on it and not head on.
We have a
Shear happens flat across, right? And that's the, like, look at the, look at the, here's something better than was first problem. There's no, so there's really not. Well, here. So we're gonna ignore that. And we calculated shear stress, but.
And.
There's no pure shear. Because it's, sorry,
I do remember like this.
You draw your stress out. Yeah. Okay, draw your stress line this off, right? So, assuming that side is, well, yeah, that's like.
We ended kind of
40,
right?
No, we had 10, sorry, 10, okay. Yeah, okay, so for context, we have a meeting with Rob and Daniela, later today. And like, we just really want to highlight student voices in on that. So if you guys could please do us a quick favor, probably what we're gonna do is, at the start of class next week, we're gonna just walk through this as a group. So if y'all could go to this slide, it should not even take 5 minutes. Please just be honest. Like, any feedback is good feedback, because we want to like make this the best course we can. And also, really what we want to do is make sure this knowledge just doesn't happen as a blip and doesn't get passed down. Like, we want good feedback on like what was useful, what was not. If you had to like teach this class or you were a McSolid CA, what would you take from this class and move it in? Yeah. Just keep it /prove. Why, yeah.
And then this is like out and
How is all the
okay, so that, but that doesn't mean and
that is good.
wait. This single line. That's, okay, so I got that. I have been, pretty much